So I wanted to explain the base 12 nature of color vision and how this could be applied to tetrachromacy. So basically we know that we have three main color receptors in our eyes, and they kind of make up, that's kind of a terrible representation there. But basically, it's hard to do this, on just your hands alone. But basically, right, you got red, green, and blue, which, we primarily evolved in a green environment. So, it might take many years for our eyes to evolve to be more red and blue sensitive, especially blue sensitive, because there's not much blue in nature, but there is a lot of blue in modern day computers and stuff like that. So this has a threeness to it. And then from this, we can get a sixness from that, because we have, blue-green is cyan, red-green is yellow, and red-blue is magenta. And what we can do is we can create other colors here, like, a more pink color that's more red-based, a orange, which is yellow-red, chartreuse, which is yellow-green, and there's an aqua, which is between a cyan and a green, and a sky sort of blue, almost between blue and cyan. And so this it goes from 3 to 6 to 12. I think it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9 decade. So yeah, you do get a 12ness there in this in these colors. But I want to show how this might work in the tetrachromatic scale. If we were to add an extra color, basically, if you didn't know, in the subtractive color model, you have the same thing, but you use cyan, yellow, and magenta. And cyan and yellow and magenta, basically, since these are subtractive colors, let's say you mix a little bit of cyan and a little bit of yellow. Well, since yellow reflects both green and blue, or green and red pigments, or green and red light, I should say, and since cyan, reflects both the blue and the green, the green is dominant, right? Two greens, are positive, and that kind of minuses out the red, and and the blue get kind of minused out, right? Leaving you with green, because these get absorbed as they are less dominant, and these get reflected. Well, a similar thing would happen in tetrachromatic color vision, because what you would have is you wouldn't have red, green, and blue. You would have red, green, blue, and a fourth color. Let's call it Viron. So fourth color is Viron. So you have 4 colors here. Okay, 4 is a multiple. It's a one of the many dividends of 12. Okay, so what you could do here from that is you could have there is you would have actually 4 primary basically subtractive pigments based off of this. And here's what they would be. You would have, there is no Y. You would have R, G, B, which we in trichromatic vision would recognize as white, but in a tetrachromatic vision, there would be more to, I guess you could say, compete with this, so it wouldn't be a simple white. The second, I guess you could say, subtractive one would be RGV. Okay. Then there would be, and these are like Trinity colors, RGV, and then you would have BV, and last but certainly not least would be BV. Okay, these are Trinity colors. These are like I call them Trinity colors because these pigments, if we could see them with tetrachromatic eyes, they would basically reflect, and you can obviously see an obvious 12ness here going on. They would reflect 3 colors at a time. And so if you were to mix this and this, see, both sides have red and green with, and the 2 oddballs are virion and blue, right? So this would equal yellow, for example. And what this would do is, you would have basically, you would have this shape here. You could have what is it? RGB here. It's kind of hard to work out because I didn't, But basically, these colors mix together to make the secondary colors. And then the secondary colors would mix together to make the primary reflective pigments. The colors in the subtractive model shouldn't be called primary and secondary colors. They should be called primary reflecting and secondary reflecting. And in this case, we have Trinitarian, reflective colors that each one of these colors would actually reflect a heap of light. It would be almost whitish. And then as you mix it together, these 4 colors, which I haven't completely gotten figured out what all of them would be, would give you this sort of look, right? So if I mixed this with this, the result would be a bluish virion, right? Because the red and the green get canceled out by the 2 positives here, right? If you have a 2 on this side and 2 on this side, it's a positive. And if you got 1 on one side and 1 on the other side, it's a negative. And that's basically how tetrachromatic color vision would work, similar to the cyan, yellow, and magenta model, except there would be a 3rd step, and you would end up having 12 colors, right? These 4 would produce 4 secondary reflecting, I should say, and then all 4 of the secondary reflecting colors would equal an additional 4 primary reflective colors, which of course would be red, green, blue, and virion.